All right, we're going to move along in our sequences section here. Now we're going to take a look at geometric series, but before we do that, we're going to use exercise 1 to make a connection between geometric sequences and functions. All right, so exercise 1 here. Robert earns $36,000 salary in his first year as an accountant and earns a 3.5% increase in each successive year. So Robert goes to college, right? He gets his degree and he wants to be an accountant. So gets a job his first year. He is going to make $36,000. That's what he starts at. Some accounting firm is going to pay him to start at $36,000 for the year. That's how much money he's going to make. But then every year they're going to say, all right, next year you're going to make 3.5% more, and then the next year 3.5% more, and then the next year 3.5% more. So they're going to get a raise every single year. That's basically what's happening here, okay? We want to write a geometric sequence formula, A sub n, that models Robert's earnings each year. So we're going to do that based on what we learned about geometric sequences in our last lesson. So it's going to be, let's recall the formula A sub n equals A sub 1 times r to the n minus 1 power. And again, we talked about why it's r to the n minus 1. All right, so let's go A sub n here. It's going to equal A sub 1, which is 36,000. And then times r. Now, r is the rate of increase. But since it's an increase, we have to add 1 to it. It's going to be, so r is going to be 1 plus 0.035. Okay, 0.035 is 3.5%. We know that by now. But if you just put 0.035 in here, it's not going to increase the money. It's going to decrease it. It's going to act like he's losing money. So we have to actually add 1. So it's going to be 1.035. By adding 1, it kind of keeps, the 1 keeps the 36,000 in place, and then the 0.035 adds that percentage to it the next year when the formula kind of works itself out. And then to the n minus 1 power. There we go. So here's A1, here's R, and here's n minus 1. It just stays because n represents the year. So now we can use that formula in Part B. We can use the formula from Part A to find Robert's salary in his 8th year as an accountant. You know, we did A1, A2, A3, A4. A5 would be his 5th year. A8, A sub 8. A sub 8 would be his 8th year. We've done this. 36,000. 1.035 to the 8 minus 1 power. And of course, that's 7, right? 8 minus 1 is 7. So I did this ahead of time to save time. If I had to punch buttons in a calculator or had to wait for you to punch buttons, we'd be here for like ever. So I did this ahead of time. Again, just type it in your calculator. If you have a calculator at home or you got your phone, you could just turn it sideways. You don't even, to raise it, you have to turn it sideways. And you should get 45,802. So he's going to start making $36,000 a year, but by his 8th year, he's going to get paid $45,800 a year. Now, what we want to do is we want to write this relationship as a function, calling it R of T, Robert's salary as a function of time. So we're going to say R of T equals, and it's going to be an exponential function, so we have to have something times something raised, right? Let me put the standard form. It would be R equals A times B to the n, or to the t, let's call it. All right, A times B to the t, where A is the starting amount, B is the rate, and then t is the time. That's just what it should look like. That's the form for an exponential function. Any exponential function looks like that. So you always remember, the starting amount always goes first after the equal sign. So in the function, you're always going to get the starting amount. That's going to be 36,000. And then the rate, 1.035. And then we're going to raise it to the t power. T, now why is it not n minus 1? Because t is right here. It's years after his first year. See, we don't need a function for his first year because we already know that 36,000 is his first year. Okay, so if we want to find, like, for example, his 8th year, which we want to do right here, we're going to say, all right, R of 7. And the reason we're going to go 7 is because it's T years after his first year. So his 8th year is 7 years after his first year. That's how you have to kind of think of it. All right, so it's basically 8 minus 1. All right, his 8th year is going to be the 7th year he's getting an increase. Think of it like that. He's not getting an increase his first year. He's starting at 36,000. He gets an increase every year. So how many increases is he getting? He's getting 7 increases. His 8th year will be his 7th increase. That's how you kind of got to think of it. That's why the n minus 1 suddenly becomes t when you write it as a function. So it's going to be 36,000 times 1.035 to the 7th, but that's going to be the 8th year. All right, again, that's going to be the same amount, 45,802.05. All right, that should not change. So that's kind of the relationship between a sequence and an exponential function. In exercise 2, what we want to do is try to find the total amount of money that Robert earned, total earnings, in his first 8 years. So he made $36,000 the first year. He made some amount the second year, some amount the third year. He keeps making more every year. The 8th year he made this, we said, but we don't know how much he made year 2, year 3, year 4, year 5, year 6, year 7, and year 7. We do know year 8. All right. If we want to find his total earnings, we got to add year 1 plus year 2 plus year 3 plus 4 plus 5. I hope everyone understands what's going on here. We're adding up the total amount of money he makes over 8 years. And that's going to be his total money. Okay, his total salary, 8 years added together. That's what exercise 2 is asking for. Well, we're not actually going to do this because down here we're going to learn an easier way to do it, but that's what you would have to do. And we could do it. We could just do this. We already know A1, we already know A1, we already know A8. We could just find A2, A3, A4, A5, A6, A7 and then add them all up. We can go plus 36,000 plus. We just add them all up. I think we understand that. But what if we could do that, right? We could do that. We're not going to do that. We could do that. But what about if they wanted his total salary for his first 30 years? Now think about how hard that would be to do. You'd have to find A1, then you'd have to find his second year salary, then his third year salary, then his fourth year salary, and you'd have to find every year's salary all the way up to his 30th year salary, and you'd have to add all those up. That right there is an example of a geometric series. It's a series of numbers added up to a certain amount, and then it'll stop. But think of how hard that would be to do. We'd have to find the salary every single year. We'd have to find 30 salaries and then go 36,000 plus, blah, 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 plus, blah, 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 plus, blah, blah, blah. We'd have to do it 30 times. That would be really hard to do. So instead of doing that, we're not going to do that. We have a formula that does it for us. And here it is right here at the bottom of your page. This is called the geometric series formula. It is given to you on the reference sheet for your Regents exam. So you won't have to memorize this. It will be given to you, but you need to know when to use it. When you want to find a sum or a total, right? All those keywords, right? Sum, okay, or total. That's another word for sum. You should know that. Of a geometric series, you would use this formula. So we're going to see some examples of where this formula would be used. So example 1 is going to be basically from the front page, that same information, right? Write a formula for his total earnings over n years. So let's say we don't do 30 years, we just say n years. So we're just going to use that formula, S sub n equals, it's A1. Now A1 is 36,000 because that's how much you made the first year, minus 36,000. All right, and then let's go back and look at that formula again. R to the n, right? and then 1 minus r. All right, so it's going to be 36,000 r. R was 1.035 to the n. I'm messing this up here. 1.035 raised to the n, and then all over 1 minus r, so 1 minus 0.035. 1 minus 0.035. So that would be it. So that's our formula. That is our Sn, our formula for S sub n. Now in Part B, they want us to use the formula from Part A to find Robert's total earnings 30 years. See how it's total earnings? All right, now on a Regents exam, they're not going to tell you what formula to use. You're just going to have to know, oh, I'm finding a total of a series. I need to use this formula. I better go to my formula sheet. All right, so S30 equals 36,000 minus 36,000 times 1.035 raised to the 30th power over 1 minus 1.035. And then that comes out to be, I did it here to save time. It comes out to be negative 65044.57377 over negative 0.035. This is negative 0.035. And then you divide this out, and you get your final answer, 1,858,416.38. Okay, 1,858,416.38. So he would make almost $2 million over the course of 30 years. I know it sounds like a lot, but 30 years is a long time. You're going to be spending a lot of money over 30 years. So that's kind of how that works. And you're going to be using this formula to answer some other questions here. So here's some other ones here where you might want to use this formula. That's a real life situation. This is just using with regular numbers. Find the sum of the first 15 terms. So it's S15. And then this is going to be, now they give us the second term is 6 and the common ratio is 4. So you could just divide those, 6 over 4. That'll give you the first term. That'll give you A1. And that's 3 over 2. So A1 is 3 over 2, which is 1.5. All right? Because, again, they gave us the second term, not the first term. But we do need the first term. The first term is 3 over 2. We'll call it 1.5. So it's 1.5 minus 1.5. And then R is the ratio 4. And then raised to the 15th power over 1 minus 4. All right, so that works out to be, and I just did this all together, except you got to make sure this is in parentheses if you're going to do that. And it comes out to be 536,870,911.5. And you might think, why is this getting to be so big? Well, think about it, guys. You're adding 15 numbers together, and these are big numbers because it's 4 to the 15th power. It's getting big. All right? So the ratio is 4. It's times 4 times 4 times 4 times 4 times 4 times 4 times 4. You're doing it 15 times, and then you're taking all those numbers and you're adding them together so that it is going to be a big answer a lot of times. You're going to get a big sum. All right, find the sum of the first 9 terms. So this is going to be S9. S9 equals, see how it's sum of the first 9 terms, S9. First term is 4, so it's going to be 4 minus 4 times r to the 9th over 1 minus r. We're missing the r. We don't know the r. All right, so I'm going to show you how to find the r when you're given the first term and, say, the 5th term. So A1 is 4 and A5 is 324. All right, A5 is 324. So I can use my formula, right? AN equals A1 r to the n minus 1. Let me get rid of this. A1 r to the n minus 1. That's my geometric formula. All right. A sub n is going to be 324. So 324 equals A1, which is 4, times r to the n minus 1. Now n is 5 because I'm using the fifth term. 5 minus 1 is 4. All right, so it's going to be divided by 4. And then 324 divided by 4 is 81. So this ends up being, I need more room here. This ends up being 81 equals r to the fourth. And then we're going to do the fourth root. So r is 3. And we needed r. R is 3. There it is. So we just put that in there. I'm just going to get rid of this for now because I need room. All right, so you throw that in your calculator. Make sure that's in parentheses. Make sure that's there. Do the top, divide by the bottom. The bottom is -2. All right, so try that out in your calculator, and you should get 39,364. Now these last two, I'm going to save example 4 and 5 for class time because actually I want to make sure we're good with this. I feel like it's a lot, so I want to make sure that we do a little bit together in class tomorrow, but this did save us a lot of class time doing this on video, so that's kind of the purpose of why I do that. But we will talk a little bit in class, and then of course you'll have time to practice these skills. See you then.